Look at a modern industrial assembly line running at full capacity. The physical reality of manufacturing is built on exact duplication. At the center of this operation is a basic economic question about scaling inputs. If you double your factory space, your labor, and your machines, what exactly happens to your total output? Now, contrast that physical factory with the modern technological equivalent, a massive, power-hungry AI server cluster running training protocols. We can represent this universal concept of doubling inputs with a single mathematical scalar. We will call it lambda, and set it to a value of 2. When applying this scalar to AI, the technology industry frequently labels the resulting growth as exponential, or praises the models for achieving economies of scale. Both descriptions are mathematically false. To decode this paradox, we have to map this out using the correct coordinate geometry. By applying the mathematics of first-order homogeneous functions and logarithmic geometry, we can show that AI scaling laws are not exponential. They are actually severe diseconomies of scale, governed entirely by strict power laws. We start with the standard microeconomic production function. Quantity of output, Q, is a function of our primary inputs, labor, L, and capital, K. If we apply our lambda scalar to multiply those inputs, we test for a condition called constant returns to scale. In the physical world, this is the cloning effect. If you have a perfectly optimized coffee shop and you build an exact duplicate right next door with the exact same equipment and staff, you will yield exactly double the output. This cloning process represents a neutral baseline state. There are no sudden technical breakthroughs, but there is also no friction from administrative bloat. This vector graph plots a standard long-run average cost curve. It measures the cost efficiency of a system as it grows. Constant returns to scale maps exclusively to the flat, horizontal bottom section of this curve. The logic is absolute. If your input costs and your total output scale by the exact same lambda factor, your average cost per unit must remain perfectly constant. In macroeconomics, this mathematical baseline is expressed through Euler's theorem, which details exactly how that total output is allocated. Under perfect constant returns to scale, total output is entirely exhausted by paying workers and capital their exact marginal contributions. The math clears the board, leaving zero excess profit and zero loss. Constant returns is not merely a theory, it is the definitive mathematical baseline for stable linear replication in any system, dictating that growth can happen without altering internal efficiency. To isolate exactly when a system deviates from that baseline, economists use a specific equation, the Cobb-Douglas production function. Look at the exponents attached to the inputs, alpha and beta. These represent the proportional output elasticities for labor and capital. If we run our expansion again and multiply our inputs by the lambda scalar, the algebraic mechanics reveals something crucial. When you isolate lambda algebraically, its exponents group together. This combined sum, alpha plus beta, is the ultimate mathematical parameter for determining the scale of a system. When this sum equals exactly 1, the system has achieved perfect constant returns. It is a linear replication. If the sum is greater than 1, you have synergy. The system yields economies of scale, where the outputs drastically outpace the inputs. But if the sum is less than 1, you have friction. The system suffers from diseconomies of scale. Physical drag or administrative bloat means every new unit of input yields diminishing returns. We can simplify this sum of elasticities by labeling it as a single general exponent, K. This transitions the concept out of classical economics and into a universal power law parameter. This K parameter is the exact mathematical boundary dividing simple linear duplication from complex system evolution or degradation. Here we have a standard Cartesian plane plotting two distinct trajectories, an exponential function and a power law function. There is a persistent misconception in the tech industry that if you take an exponential growth curve and compress the horizontal x-axis logarithmically, the curve will form a straight line. To test that, we first create a semi-log plane by compressing only the y-axis. Notice that the exponential curve instantly straightens into a perfect diagonal. This specific straightening reaction on a semi-log plot is the definitive geometric proof that a relationship is truly exponential. If we revert the graph and test the misconception by compressing only the x-axis, the exponential curve distorts. A log x plane only linearizes a simple logarithmic function. Now watch what happens when we compress both the x and y axes simultaneously into logarithmic scales, creating a log-log plane. The power law function snaps into a perfectly straight line. The underlying algebra requires this geometry. Taking the logarithm of a power law creates a strict linear relationship between the logarithms of both variables. And the visual slope of this straight log-log line is not arbitrary. Its slope is the exact numerical value of the exponent k. The rule is absolute. If empirical data forms a straight line on a log-log plot, it is categorically a power law. The system is governed by scale-invariant proportional limits, not an exponential explosion. This is a standard chart reflecting the chinchilla scaling law, plotting AI training compute against model loss. If you look closely at the tick marks on both axes, you will see they are spaced logarithmically. We are looking at a log-log plane. We can map this directly back to our Cobb-Douglas production model. The compute acts as our primary input, and the reduction of loss serves as the proxy for our output. The mathematical scaling formula governing this straight line proves it is a pure power law. When we analyze the exponent parameter k for AI loss, it sits at a very small fractional value, typically between 0.05 and 0.2. It is significantly less than 1. The practical reality of a k less than 1 is brutal. To have the error rate of a model, an organization cannot simply double the compute. They must increase their compute exponentially to achieve a fractional gain. Because the AI parameter strictly falls below 1, modern scaling laws mathematically reside deep in the domain of severe diseconomies of scale. Every single unit of performance is aggressively more expensive than the last. This leaves us with a final narrative paradox. If training an AI represents such a severe diseconomy of scale on paper, why do technology leaders voluntarily incur these massive costs? We have to map the brutal cost inefficiency of the power law on the left against the actual functional capabilities the models acquire on the right. Classical production economics strives for perfect cost efficiency. The goal is to reach a k of exactly 1 and coast. AI development operates under an entirely different logic. Developers willingly pay the exponential compute penalty to push the system until it manifests nonlinear, emergent capabilities, like zero-shot reasoning or complex logic parsing. Any deviation from k equals 1, whether through physical friction or cognitive synergy, signals a system that is changing its internal structure rather than simply cloning itself. A value of exactly 1 is the mathematical limit of simple replication. AI scaling demonstrates we are willing to accept severe mathematical inefficiency, brute forcing a power law, to trade raw compute for the emergence of qualitative intelligence.